So in the last lecture and the one before that, we looked at field equations. We wrote them down. We discussed some general aspects, but there's more to say about them. And in particular, one of the interesting things that we're going to look at briefly today is the counting of degrees of freedom. That is, how many degrees of freedom do you actually have in this theory? Now, you remember that the theory, of course, is based on a metric, right? G mu nu of x. And that this metric satisfies these field equations, right? R mu nu minus 1/2 G mu nu R is equal to minus 8 pi G times T mu nu, right? So we can count how many degrees of freedom we have in the metric, right? And we have 10 because it's a symmetric tensor, right? So there's 10 independent components. And when we look at the field equations, everything seems to be perfect because the field equations also involve symmetric tensors, the R mu nu, the G mu nu, and the T mu nu. And so there's 10 equations, right? So there's 10 degrees of freedom here, and there's 10 equations, right? And so that means that presumably we can solve for all components of the metric. But that turns out to be, of course, not correct, right? And the reason why it is not correct is because these equations are not all independent. They're not all independent because of the Bianchi identity, right? We do know that R mu nu minus 1/2 G mu nu R, right? That semicolon of that nu is equal to 0, right? So we do know because of the Bianchi identity that in fact we have 4 constraints, right? There are 4 equations. So that would look like a problem because we have 10 degrees of freedom but only 6 equations because of the Bianchi identity constraint. But in fact, that is not the case either because we have general coordinate invariance, right? General coordinate invariance implies that we can go from one coordinate system to another one, right, by changing coordinates. So that means that we have a freedom to redefine the metric, right? And as a result of that freedom, we actually have 4 less independent degrees of freedom, right? Because we can have 4 coordinate transformations, right? And so that looks like it's solving the problem, right? Because we have initially 10 degrees of freedom for the metric, but under general coordinate transformation, we can transform the metric in such a way that kind of the physics remains unchanged. And at the same time, we have 6 equations to determine those 6 components of the metric. So this is analogous, of course, to, once you think about it, is analogous to what happens in electromagnetism, right? Because in electromagnetism, we have the same issue, which is the issue of gauge invariance. Right, so we have originally, right, if we look at electromagnetism, right, then we have d mu, or let's say d alpha, let's use this Lorentz indices, f alpha beta is equal to minus j beta, right? And now we can write this field in terms of the vector potentials, right? So we can write this as, right, in terms of A alpha. We can write this as box, right, box of A alpha, and there's an extra term which is d alpha, right, d dot A is equal to let's say minus j alpha, right, in this case, and now we can use a gauge, right, such that d dot alpha is equal to 0. So we impose a gauge condition. We impose a gauge condition, and that is what we do in electromagnetism all the time because that gauge condition is usually picked in order to simplify the equations, right? So if we simplify the equation this way, because of this extra term, it's natural to use this, right? And so as a result, we have just that box, A alpha is equal to minus J alpha, right? And that is, of course, much simpler. We have just an ordinary wave equation with a D'Alembertian, right? And the result of that, the solution, I'm sorry, is immediate because you can then write A alpha as minus 1 over box acting on J alpha, right? And this solves the problem completely. Usually one has to be careful because in this case one has to pick up the retarded potential, right? So one has to pick the retarded part when you invert the Laplacian, or the D'Alembertian, I should say, right? So this is what happens in electromagnetism. And as a result of that, in electromagnetism, we have only 2 degrees of freedom because we start out with the A alpha, right? And there's 4 degrees of freedom there, right? And then we subtract, right, -1, which is from the gauge condition, which is d dot alpha is equal to 0. And then there is a residual invariance, right? You can still do a gauge transformation with that. So it's 4 minus 1, which is 2 degrees of freedom, right? And this is, in fact, we know is the correct counting of the degrees of freedom for the electromagnetic field because we know that you only have 2 transverse polarizations, right? Or in quantum mechanical languages, you have a photon that only has 2 spin projections, right? And so the question is, how does this translate into the case of gravity, right? Which is not just an academic question because it is of practical importance. Practical importance because you want eventually to reduce the equations for the gravitational field to the simplest possible form. Simplest possible form. So that means that you want to impose some sort of a gauge condition, right? And so that gauge condition would like the field equations, right? You like to reduce the field equations to something that looks, under appropriate circumstances, which turns out to be weak fields, to something that looks like the electromagnetic field equations. That is, you would like to write that, and usually you write the metric as g mu nu plus eta mu nu plus h mu nu, where this is small in some sense, right? You would like to reduce the field equations to something like box h mu nu is equal to minus 16 pi times g times t mu nu. Right? You would like to force in this form, and of course none of that looks like that yet, right? And the reason why you have to use the weak field expansion is because in general the equations of gravity, of course, are highly nonlinear, right? You start out already from the metric itself. At some point you need the inverse metric, right? An inverse metric involves the determinant of the g mu nu, so then you have all sorts of terms that are not linear in the metric. So you have to do some sort of weak field expansion, as we'll see in a moment, or in a few lectures. But even when you do the weak field expansion, you're going to get lots of terms that don't look particularly transparent. So you want to impose some sort of gauge condition so you can force it in this way, right? And in fact, we will be. Right? We will be able to force it in this way. The only slight modification is that, in fact, what appears here is not the t mu nu, but is the t bar mu nu, right? So t bar mu nu is equal to t mu nu minus 1/2 g mu nu times t lambda lambda. So in other words, the source for the gravitational field is not going to be the t mu nu, but it's called trace reversed form of it, which subtracts the trace. But that's kind of not very important at this point. So if we are in this situation, then of course this is great, because then that means that h mu nu is going to be equal to minus 16 pi g times 1 over the box times this t bar mu nu. And we have basically been able at that point to write the gravitational field in terms of the sources in the same way that you do in electromagnetism, right? So if you assign me, right, distribution of energy in some region, right, which is this t mu nu or the t bar mu nu, then from that distribution of energy momentum, I can construct the field everywhere by doing a process which is similar to electromagnetism. So the question is, how do you reduce the original field equations, right, to something that looks like this? And that requires a gauge condition, right? It requires a gauge condition. So this gauge or coordinate condition is, well, it's going to be something, of course, that breaks general coordinate invariance. Because in electromagnetism, when you impose a gauge condition, right, such as divergence of A is equal to 0, that does break gauge invariance. And of course, that's the whole purpose of it, so that you can reduce this gauge freedom to just a single point on the orbit. So here we have something similar, right? And so what is the coordinate condition that we should write down? Well, it should be one that simplifies the equations as much as we can. And of course, it's going to give that box A equal to the source. And so at this stage, we don't know what that form is, but it turns out that a suitable one is that gamma lambda is equal to 0. Right? This is a good coordinate condition. And so this means that gamma lambda, so mu, so that means that we take the affine connection, right, and we contract on those two indices. So that is the condition that will do the trick for us, right? And right, so G mu nu gamma lambda mu nu is equal to 0, where this gamma is the usual g to the minus 1 times dg plus dg minus dg. So it's going to be some constraint on the metric, which is not particularly transparent, right? Because the g is not, the gamma is related already in a complicated way to the g. But it turns out that if you look at the weak field limit, so again, right, you write g mu nu is equal to eta mu nu plus h mu nu, where h mu nu is small, then in that limit, by using the definition of the affine connection, you just get that this is the same as d mu h mu nu is equal to d nu h lambda lambda times 1/2. Like this, plus terms which are of higher order in h. So, of course, this looks a little bit, right? It looks a little bit like the condition we have in electromagnetism, which is d mu a mu, or d alpha a alpha is equal to 0. Right? It looks a little bit like that, but not quite, because we have a term which is like that part there, and then we also have one that involves the trace. So this is called a harmonic gauge condition. Harmonic gauge condition. And at first it's not obvious why it's called a harmonic gauge. It turns out that in this set of coordinates, because when you fix a gauge in this way, when you impose, remember, gamma is not a tensor. Right? Gamma is not a tensor, right? It's coordinate dependent. So by requiring that gamma has that form, you're fixing a coordinate system, right? It is a general feature of general relativity that it is a coordinate invariant, that the theory is formulated so different observers using different coordinate system write down the same equations, but you can in fact choose a coordinate system by imposing one of these conditions. And so imposing that condition means choosing some sort of coordinate system. And by a little bit of algebra, you can actually show that in this coordinate system, you have that box x mu is equal to 0. So the coordinates satisfy the wave equation, therefore a harmonic. So that is why it's called a harmonic gauge condition. For our purposes, what we'll mostly be using is this relationship in the weak field limit, because it is this relationship that gets rid of all sorts of terms which don't make the wave equation transparent, and just gives us the box h equal to something, right? So it makes, in fact, there's 4 terms altogether when you write down the left-hand side of the field equations, and 3 of those cancel out in the harmonic gauge, and you're just left with box h. Box h mu nu is equal to what I just wrote before. So this condition is a useful one, and it is one that we will consider in the future. Now, it turns out that you can actually, just let me mention that briefly, because I think over the years people have been interested in what happens to gravity in d dimensions, right? And so if you are in d dimensions, you have, first of all, you have the metric, right? And the metric in d dimensions has d times d plus 1 over 2 components, right? That's how many components there are to the g mu nu, right? For the simple reason that it starts out as a d by d matrix, right? But then it's symmetric, right? And now, if you subtract this coordinate condition, well, this coordinate condition, it's obvious that when you write down either that or this, right, it's the same thing, then you have the equations, right? So you have that the original 10 degrees of freedom of the metric in 4 dimensions is reduced by 4, right? And you still have a residual invariance, which is some additional coordinate transformation that you can do. It's easy to see, for example, again, in the weak field limit. And so you get that the number of degrees of freedom is equal to d times d plus 1 and then minus d twice. And so this is 1/2 times d minus 3. Okay, so you come to the conclusion that through this argument, which is just a repetition of what we just did, but in d dimensions, you have that the physical degrees of freedom of the gravitational field, well, in 4 dimensions, it's 2, because you take 10 minus 4 again, and you get 2, and that's in fact the same degrees of freedom as the electromagnetic field, which is remarkable, even though you do have a spin 2 particle, but you only have 2 helicity states for the gravity, and you only have 2 independent polarization states for the gravitational field. So in 4 dimensions you get 2, but if you go down to 3 dimensions, then the number of degrees of freedom is 0. So in other words, gravity does not really exist in 3 dimensions. So 4 dimension is the first dimension where something interesting happens. You can't have gravitational waves in 3D. Right? You have to go to 4. So 4 dimension is the first case, right, where we have interesting gravitational interactions. In 3 dimensions, all the interesting aspects of the field equations go away, because the field equations in 3 dimensions are still in a vacuum, that the Richie tensor is 0, but when the Richie tensor is 0 in 3 dimensions, the Riemann tensor is also 0, so you get nothing, you just get flat space. Right? So, well, it's a good thing that we live in 4 dimensions, otherwise, you know, there wouldn't be much of an interest in gravitational physics. So what else was going to say? Oh, yes, there is one last item, and that is that you can rewrite this because you are taking these indices and tracing them over. You can actually rewrite this as a divergence. So this can be rewritten as d by dxk of square root of g, and then g lambda k is equal to 0. So there is, in fact, a simpler form, which is directly in terms of the metric, right? Because this one is implicitly through the definition of the affine connection. So it is some sort of a 4 divergence that is equal to 0, and you can write it in this form. And so that was one issue that I wanted to discuss, is what happens to the number of degrees of freedom in 4 dimensions. Again, to say it one more time, the remarkable thing about the theory of gravity is that just to some extent, as in electromagnetism, you start out with a huge number of degrees of freedom, because 10 is a large number. So you have 10 independent components of the metric, but then because you have all this symmetry in the theory, right, because of this general coordinate invariance, it turns out that the actual number of physical degrees of freedom is much less. It's just 2, right? And so that is all related to the fact that the theory has this local invariance. If you don't have the local invariance, then of course you don't have these identities, you don't have the Bianchi identities, you don't have the freedom to redefine coordinates, and you don't have a massless spin 2 particle, which is what has 2 degrees of freedom only. All right, so it's all tied in. And now, the other aspect that I wanted to discuss briefly today is, which is related to what we just talked about, is what happens if you have a gravitational field that goes to 0 at infinity. So you can think of some distribution, right, where T mu nu is different from 0 in some region, right? And we assume that that region is finite, and then we look at what happens at very large distance from it. So we are at some point here, which is called x, right? And we assume that the metric g mu nu of x, right, as x goes to infinity, that, well, that space-time becomes flat. So we're basically thinking of a universe that's empty. There's nothing in it except for that mass distribution at some point, right? So g mu nu, as x goes to infinity, just turns into eta mu nu, right, which is a flat metric. Right? And, well, the real universe, of course, is not like that. Right? If we go out at infinity, there's always some mass distribution that plays a role. But nevertheless, from a mathematical point of view, we can talk about this. And if this is the case, then there's certain results you can derive from it. And obviously, this is a nice case to play with, right? A case where the fields all go to 0 at infinity, right? We have flat space at infinity. And we only have some matter or energy distribution, which is localized in a given area of space. And so again, we have to, well, in this case, we write again that g mu nu is eta mu nu plus h mu nu, right? And so what we know now is that h mu nu goes to 0 at infinity. So as x goes to infinity, now we know that this perturbation vanishes. And now what we can do at this point is, remember, we want to kind of get some sort of insight into the field equations, right? So which I'm going to rewrite up here, right? R mu nu minus a half g mu nu r is minus 8 pi g T mu nu. And we have lambda equal to 0 for now, right? At some point, I think it will be interesting and relevant to introduce a cosmological constant term, which we know is non-vanishing. But nevertheless, that cosmological constant term is very small and only plays a role when we go to very large distances that are relevant for cosmology. So for now, we have this lambda equal to 0. And this equation is not particularly intuitive. It is not easy to see what the different ingredients to it are. In other words, how does the metric appear in it, right? Because the problem is that, of course, the R, right, is something like d gamma minus d gamma, the Riemann tensor, right, plus gamma gamma minus gamma gamma. So the Riemann tensor is some complicated, not too complicated, but fairly complicated expression in terms of derivatives of the affine connection. And the affine connection itself, as I said, is 1/2 times g to the minus 1 times dg plus dg minus dg. So it itself is some combination of derivatives of the metric with an inverse of g on top of that in front. So it's not particularly transparent to see, you know, how the metric appears in the field equations and what happens under what conditions, right? Well, one of the conditions under which we can understand a little bit more of what is going on is precisely this case. Because if we do assume that the field is weak, then we can start expanding, right? We can start expanding because we look at the derivative of the metric. For example, the derivative of eta is 0 because eta is a constant, right? So we get derivative of h. And the g to the minus 1 is 1 over 1 plus h, which is essentially 1 minus h, right? So we can expand this here. And then we plug that expansion in there, and we keep on expanding. And in the end, you get something that is much more tractable, right? You get an expression that instead of having determinants of the metric and things of that sort, involves much simpler combination of the h, right? So the first thing we have to figure out in order to do this sort of expansion is what happens to this piece here, right? So what happens to this piece when you do the weak field expansion, right? And so this is something that you can patiently work out. And let me make a little bit of space here, right? So we look at the linear part. The linear part of, right, we want to see the piece that is linear in H. Right? That's the dominant term when H is weak. And what we need to look at is the linear part of the Richie tensor, because this other part is just a contraction, so we can do that easily. So linear part of Ricci, right, R mu nu. And so for the linear part, we're going to give a name, right? And so we're going to call it 1. And so R1, linear part, it will have indices again, mu and kappa. And so using the definition, now we start to turn the crank and do a little bit of algebra. And so this is equal to 1/2. 1/2 is coming, right? This is 1/2 there. So 1/2 times various derivatives of H. So for example, the second derivative of H lambda lambda, right, with respect to x mu, with respect to x mu and xk, right? And then minus the second derivative of H lambda mu, derivative with respect to x lambda and xk, right? And then another term, which is the derivative, the second derivative of H lambda k, derivative with respect to x lambda and x mu, right? And then plus the second derivative of h mu k with respect to x lambda, twice, one upstairs and one downstairs, right? And then close parenthesis. So you see, even if you look at the linear term, right, the linear term in H of just this piece here, right, just looking at that, it is not too simple. It is not too simple, right? It contains 4 terms. And now we're going to give it a name and call it R1, so the linear term in H in the expansion of the Richie tensor. But nevertheless, based on what we discussed a moment ago, it turns out that if you impose the harmonic gauge condition, right, then in the harmonic gauge, what happens, and we can state that already here, and you can verify that, again, it's a little bit of algebra, that the first 3 terms cancel. The first 3 terms cancel. So if you use the harmonic gauge condition, then it is nice that the only term that survives is, so these cancel out, right? And the only terms that survives is the last one, right? And you recognize that the last one is, first of all, it has the same indices mu and k that appear over on this side, same indices for the metric. And the other thing that you see is that it has the derivative with respect to x, the same x, twice, and then traced over. So this is nothing but box h mu k. That's a box h mu k, right? So by doing this linearized expansion of the Richie tensor, you recognize right away that the harmonic gauge condition is a very good choice, because the harmonic gauge condition gets rid of all this junk, right? It gets rid of all this junk, and what's left over is what you would like to have, which is just the box operator, just a D'Alembertian like you do in electromagnetism, right? And so now we'll use this when we talk about gravitational waves, right? The wave equation for gravity in a little bit. But at this stage, we just are going to hang on to the whole thing, right? Have the whole expression. And so what can we do? Well, we can do the following. We can do the following. We can try to force the field equations we can try to force the field equations in a way that looks like the equations of electromagnetism, right? Remember, in electromagnetism, if you do electromagnetism, then you just have a box A alpha, right? A alpha is equal to minus J alpha, right? You can write it in this form. And so that's what we would like to do here. And so what we do is take this expression for the linear part of the Richie tensor, right? So it's R1 mu k, right? Well, that's not the whole field equation, because the field equation does not contain just the Ritchie tensor, right? It contains also this other part, right? But we have the linear part of that, and then of course we have the linear part of the Ritchie scalar. So we write that as minus 1/2 eta mu k, right, times r, and that's the linear part of the Ritchie scalar, R1. Okay, so again, to emphasize, this is of order h, and that is also of order h, right? And as far as this expansion is concerned, the g mu nu here, because this is already of order h, the g mu nu here can just be the flat metric, which is the eta, right, the eta. And we're going to write this as minus 8 pi g times, well, we certainly have the T mu nu, right? The indices here are mu k, but other than that, it's the same thing. So T mu k, right? But of course, if we stop there, then that's not the whole equation, right? So what do we have to add on the right-hand side? Well, of course, we have to add everything that we've left out to this stage, right? Which is the higher order parts, right? So the higher order parts, we're going to call them T mu k. So all higher order parts in H, right? So what are they? Well, T mu nu, or T mu k, is defined to be everything that we left out. So in other words, everything that on the left-hand side of the field equation is not of order h, we're just going to move it over on the other side, right? And when we move it over the other side, though, we are going to have a g in front, so we better divide out by a g here. So we have that this is equal to 1 over 8 pi g times what? Well, times everything else that we left out. So everything else that we left out is the original r mu k minus 1/2 g mu k times r, right? Obviously, minus what we included explicitly here on the left-hand side, which is just the linear part, right? So minus r1 mu k plus 1/2 g mu k times r to first order, and then close parenthesis. Right, and in fact, to be consistent, because we used an eta there, we should use the same thing here so that we have exact balance between left and right-hand side. So this should be eta mu k, right? And so what is this object? Well, obviously, this part here is the matter, right? The T mu nu, or the T mu k, is the usual contribution from matter fields. So we see that when we bring everything that is not linear in H over on the right-hand side, we end up having something that looks like the energy momentum tensor of the gravitational field. So this is the gravitational field contribution. Gravitational field contribution, right? So we have a piece that adds to the T mu nu of matter. Now, there is something we know about the T mu nu of matter, right? We do know that the T mu nu of matter semicolon nu is equal to 0, right? So we do know that the energy momentum tensor of matter has a covariant divergence which is 0, right? And that is one of the fundamental ingredients in the field equations. And in fact, it requires that the Bianchi identity also be there on the left-hand side. And but what about the little t? Well, the little t is not conserved, right? The little t is not conserved because we decided to basically split up something that was the original left-hand side of the field equation, to split it up into a linear part and the rest, right? And that splitting, of course, does not give us a tensor. That splitting does not give us a tensor, right? So this part here is not conserved, right? This part here is not conserved. So we cannot talk about it as being a genuine tensor in any way. Nevertheless, it is the gravitational field contribution to the right-hand side of the field equations. So there are a number of properties that one can work out from this way of writing the field equations, because notice in particular that no approximation has been done so far, right? By just splitting up the Ritchie tensor into a linear part and the rest, that is not an approximation in any way. That is something you can do. It does look a little bit ugly because, as I said, you're breaking it up in pieces that are not individually conserved. Nevertheless, you can do it. And what do we learn from this, right? So first of all, we can do this expansion to any order, right? So we can write to any order in H, right? We can write R mu k, right? R mu k as the R mu nu, or R mu k 1, which is of order H, right? And we can write it as R mu k, which is of order H squared if we have a 2 up there, and then plus R3 mu k of order H cubed, etc. Right? So we can certainly split it up in different parts, and usually if we are interested in weak gravitational fields, then it would be enough to just stick to the quadratic order. And so if we do that, then this allows us to define, for example, tau mu k, which is t mu k plus the little t mu k. And if we do that, then this is the energy momentum tensor for matter, right? And the t is what we defined over there to be the contribution from gravity, right? And then what appears, of course, in these field equations that are expanded out, maybe you can put a box around this, right? What appears on the right-hand side is, of course, the sum of the two, right? And so this would be the total that we have here, right? And so this would be what we would refer to as the tau. So this part here is this tau mu k, right? Which is, so in other words, when you force the equation to look like the equation for electromagnetism, then you find that on the right-hand side you have two source terms. One source term is matter, and the other source term is the gravitational field, which is also a source, right? It is also a source. Because of the nonlinearity of the field equations, you have, in fact, infinitely many terms, right? This expression here has an infinite power series in H, right? It doesn't terminate, it goes on indefinitely because you have this complicated nonlinear dependence on the metric, right? And so this is all nice and allows one to define, for example, the P mu, the total energy momentum for a distribution of gravitational fields. And one can show, which I won't go into because we don't have a whole lot of time, one can also show that if you have a purely gravitational field, then if you have just pure gravity, then the energy associated with that for fields which are asymptotically go to zero, the energy is zero. It's called zero energy theorem. And if you have also matter, then this quantity is positive, is always positive. So there are a number of theorems that you can prove if you have fields that are asymptotically flat, and so that's kind of interesting. And we'll come back to some of these discussions when we talk about gravitational waves, because gravitational waves are, of course, the simplest instance where you want to look at what happens to gravitational fields that are far away from some matter distribution, where the field is usually sufficiently weak that you can do this expansion, right? There are cases where the field is not weak, right? Because if you have a black hole, the field is not weak. And in fact, the remarkable thing about Einstein's theory is that there are certain cases where, in fact, you can get an exact solution without ever assuming that the field is weak. Because if you always had to assume that the field is weak to get anywhere, then, of course, you always worry about all the things you left out, right? But in the case of a black hole, the Shortcharge solution, you can get an exact solution without assuming that the field is weak. And in the case of the Kerr metric that Ben is going to talk about at the end of the class, you can also get, which is a rotating black hole, you can also get an exact solution without assuming that the fields are weak, right? But normally to get anywhere, it's tough, right? Because if you don't have any sort of symmetry, then solving these nonlinear, non-polynomial because of the determinant of the metric and so forth, and inverse of the metric is non-trivial, right? So then you have to, in some cases, you can just use the weak field expansion if the field is weak, and that will get you somewhere. So we're going to leave this business of trying to understand what the field equations look like. Again, to summarize what we have learned from the discussion that I did in the last few minutes is that you can indeed force the field equations to look a little bit like electromagnetism. But when you do, so that you have this box H term, then you have a source term which is not just the T mu nu for matter, right? The gravitational field is also a source for itself, right? Because the gravitational field, if you have a field distribution somewhere, that carries energy and carries momentum and therefore is a source for itself. That never happens in electromagnetism, right? Because the photon, as it propagates, doesn't carry a charge, right? The photon does not carry a charge, so it is not a source for the electromagnetic field. The electrons, right, objects that have a charge are the source, but not the photon. And as a result of that, it's a linear theory. So in gravity, we don't have that luxury, right? In gravity, you have that everything's charged, right? Everything that exists has energy and momentum, and that includes the gravitational field itself. So the gravitational field is a source for itself. As a result of that, of course, the equations are highly nonlinear, right? It's expected. It should be that way, right? And Einstein's equations are simple, right, when written in terms of Ricci and so forth, but nevertheless, if you look at them closely, you can see that there is a lot of complicated structure in them. And one way of looking at what the structure is through this weak field expansion, where you introduce the T mu nu and bring it over on the right-hand side. So I think we are done with the kind of general discussion of the field equations for a little bit. And so we are going to talk about next, classical tests of general relativity. Even before that, some solutions, right? Solutions of the field equations, which we can obtain in simple situations. So the first case, of course, will be the case of a static isotropic metric, which is the analog of the Coulomb field in electromagnetism, right? So the question is, if you put a point charge at the origin, what does the field look like? If that charge is stationary and doesn't do anything, right? You'll expect to have a field which is time independent. And in fact, by symmetry, it should be a spherically symmetric field. So here, the notion of a point charge is replaced by energy momentum distribution at the origin, right? A mass that is placed at the origin. And presumably, when you do that, when you have a delta function at the origin, that means, of course, the energy momentum tensor is zero everywhere except at the origin. So you're basically solving just a vacuum equation, right? r mu nu equal to 0. And so if you do that, then that's the Shortcharge solution, right? And from the Shortcharge solution, we can get a lot of mileage out of it, because that, of course, describes, for example, the solar system to a good approximation, right? The sun is a body that, to a first approximation, if you're far enough from it, you can consider it as a point source, and then there's all sorts of other astrophysical objects which are described by the Schwarzschild metric. So we are going to look at solutions of the field equations and then discuss some of the standard tests, not in great detail because of lack of time, but so classical tests. Classical tests of GR, right, will include things like, well, the very first one was the precession of the perihelion of Mercury. Because it had been known for a long time that there were anomalies in the motion of Mercury. In other words, the perihelion of Mercury was known to precess, and some of that was due to perturbations from Venus and other planets, right? And when all of that was accounted for, there seemed to be a discrepancy. So there was a long, well-known discrepancy between the theoretical calculations based on Newton's theory, right, and what was actually observed. And that discrepancy is a precession of 42 arc seconds per century in the major semi-axis of the motion of Mercury. And so general relativity gives exactly that amount. So that was kind of nice that Einstein worked that out very early on. Even before he had the final formulation, he already had figured out that you would get that amount from just, again, of course, looking at weak fields, because it's enough when you look at the gravitational field of the sun, you can do a number of approximations and get the correct answer, more or less. And so that's kind of a classical celestial mechanics calculation done with a modified potential, which is the potential that you get out of GR, because there's extra terms, of course, in the gravitational potential. So the other thing that he immediately predicted was the deflection of light by the sun. So that had not been known. 1916, it was not known that there could be such an effect. He was the one that predicted it. This was during World War I, so there was no way that any of this could be observed, because you needed a solar eclipse in order to see the motion of the stars as the light just goes by the sun. But it was done soon after the war in 1919. Eddington went out to Brazil and observed deflection of light by the sun during a solar eclipse. There's other effects which were discussed later on. So, for example, some sorts of time delays and radar echo delay. Radar echo delay from various spaceships that travel around the solar system. You can look at effects that are predicted by GR, and in fact, again, these effects seem to be in agreement with what GR predicts. More recently, one has been able to put gyroscopes in orbit, so you can look at the precession of gyroscopes in orbit. Right? Again, GR makes some very specific predictions on what should happen. There's a number of different effects, which in atomic physics we usually call L.S and spin orbit and hyperfine splitting and things of that sort. There's an analog of that in general relativity, which has to do with geodetic precession and frame dragging. So those are effects that are precisely predicted by the field equations, if we do know what the gravitational field of the Earth looks like and so forth, which we do to a good extent. And then we have, of course, the prediction of gravitational waves. So detection of gravitational waves would be another major test of general relativity. not only the detection, but also showing that you do get, in fact, the right polarization states for it. General relativity, as I mentioned before, predicts that there's only two helicity states for the graviton, that there's only two polarization states for a gravitational wave. And if you observe three, then that means that it's not quite Einstein's theory. There's something else is going on, right? It's like in the case of a photon, if Maxwell's equations are correct, then there's only two transverse polarizations. So if you find a third one, then there's a problem with Maxwell's equation. It means the photon is massive, for example, right? So detection of gravitational wave is a major test that is coming up at some point, right, when they find these things, right? So there's a big detector that is operational, LIGO, and there's another one that's planned, LISA, in space. And finally, another verification of the effects of general relativity on very large scales are, well, part of it, of course, is cosmology, but certainly also gravitational lensing. Gravitational lensing is a very direct way of seeing that light is deflected by strong gravitational fields, such as the ones from a galaxy or a black hole, right? So anyhow, we're going to start here somewhere, right? So in this case, we will be discussing effects that are due to the sun, right? The sun can be approximated as a body that is pretty much static with a field that is isotropic. So it does make sense to try to find solutions to the field equations for a static isotropic metric, right? Now, most books, such as Weinberg and Misner-Wheeler, go into a long discussion of how you can actually show that if you do have a static isotropic metric, then it can always be brought in a certain form, which is a simple one in terms of two functions, a and b. And that is done by a suitable, so you first write the most general static isotropic metric, which will involve a number of functions, like 4, which you can call a, b, c, and d. And then you can do suitable coordinate transformations to make it simpler. And you can also redefine the time. Right? So you can redefine the time and reabsorb some of these functions. And so when you do that, right, static isotropic metric, right, you can bring it eventually into a kind of standard form, which is that d tau squared, right, is equal to some function b. And because it is static, everything is going to depend only on r and not on t, right? So there's no time dependence, right? And the question is whether, of course, this is a solution of the field equations. And the answer is yes, it works, right? So it's some function that depends on r only for dt squared, right? And you got to have that in, otherwise you can't find a solution, right? And then minus some other function, again, which is only a function of r times the r squared, right? And then plus the angular part. And because we're assuming that you have spherical symmetry, the angular part is simple, right? So minus r squared d theta squared plus sine squared theta d phi squared, right? So this part here would be described as the d omega squared, right, for example. Right, so the point is that b of r and a of r are t independent, time independent, right? And so this is what Schwarzschild first fiddled with, right? Schwarzschild. (1916), so just about as Einstein was writing down his field equations, he already sat down and tried to find a solution to the field equations that has this simple form for the line element or the metric. Now you do remember that in our notation, right? You do remember that in our notation, d tau squared is minus g mu nu times dx mu dx nu, right? So in other words, the line element is given by components of the metric times the increments in the coordinates. So in this case, the increments of the coordinates is just dt, dr, and of course d theta and d phi, right? So you can read off can read off the g mu nu from that, right? And so the GTT or G naught naught is equal to this thing, okay? And the GRR is this one, and then the G theta theta and G phi phi are given by these other matrix elements, right? So GTT. So instead of calling it G naught naught, we just remember, right? We want to remember what the indices refer to. So we have this GTT, and that's equal to minus our function B of R, right? And then we have the GRR, which is A of R here, right? And then we have the G theta theta, right? Which is just sine squared, R squared, right? And the G phi phi, which is R squared sine squared theta. Okay, and that's all there is to it, right? That's all there is to it. And so that means the metric is diagonal. Right? Diagonal, so that makes it particularly simple. All sorts of matrix elements of the metric are 0, which means that lots of components of the affine connection are 0 because the derivatives vanish, right? Because the G is 0 to start with. Everywhere except along the diagonal, right? The other thing, of course, that is very easy to work out is the inverse. Because if you have a matrix that's just diagonal, then the inverse is trivial because it means you just take the matrix elements along the diagonal and invert those, right? So we have, So we have the GTT. You see now the indices are upstairs, right? The GTT is minus 1 over B, right? And the GRR, again with the indices upstairs, is 1 over A, right? And of course the other two, same story, right? So the G theta theta is 1 over R squared, and the G phi phi, upstairs of course, and the G phi phi is 1 over R squared times sine squared theta, all right? So working out the inverse of the metric is not a big deal in this case. And you can work out, for example, the determinant. Well, the determinant is just a product, right? The determinant is just a product of these along the diagonal, the non-zero matrix elements. And now you can start calculating, right? So, for example, gamma t, right? So we're going to use indices that are t, r, theta, and phi. So gamma t, tr is gamma t, rt. Of course, the affine connection is always symmetric. And so this is equal to b prime divided by 2b. All right? So, well, this looks like a lot of fun. In this case, it's easy because the metric has such a simple form, and one can calculate all these components. But we're going to do it differently. So we are going to enlist the help of our good friend that is going to allow us to calculate these things using computer algebra. Now, in this case, of course, you can do it by hand because it's just a matter of patience of using the definition of the affine connection and calculating all the non-zero components and then doing Ricci from that. Remember, by the way, that we are going to solve, right, as I will say in a moment, we are going to solve the equation. Well, we do have r mu nu minus a half. Remember, the cosmological constant term for now is 0 because in solar system scales it's kind of irrelevant. And so we are going to solve r mu nu minus a half g mu nu is equal to minus 8 pi g times t mu nu. But we are going to deal with a point source at the origin. Right? So this delta function here, and then everywhere else it's 0. Right? So we basically just want to solve the equation of this equation like this equal to 0 everywhere except at the origin. So we're basically dealing with vacuum solutions that then have the appropriate boundary conditions, R, of course. And but then we can relate one to the other. So we are just, as I discussed in a previous lecture, we just have to solve r mu nu equal to 0. Okay, so that's the equations. That's the equation we are going to use. So here is a Mathematica notebook that actually helps us out in calculating all the things that we need to calculate when we are given a metric. So the first case I look at here is, in fact, a generic metric. Right? So a generic metric, which I call G here, but actually the components are called H for notational convenience, depends on 4 coordinates, x1 to x4, right? And so it has this form. It's already symmetrized, so you can see it's actually a symmetric matrix. And it's given in this form, and so you can look at, let's see if this works. Yeah. So actually I should stay on this side. So one of the things that you can calculate is the determinant of this metric. And already when you calculate the determinant, you get quite a few terms, right? And we haven't even started. Right? We haven't even started to calculate components of the affine connection or any of that. So that comes here, right? And so this is the definition we use, which is the same as the one we employed in class, right? Except that once you think of it, defining the affine connection and those derivatives involves the inverse of the metric, but the inverse of the metric is just the inverse of some matrix, right? So that is what is done here. We calculate derivatives, right? And we have indices, which instead of being called mu, nu, lambda, sigma, are called A, B, C, and D, right? So the metric has indices A here, and A and N, B and N, and G, A, and B. And then we take the derivative with respect to another index. And then, of course, at the end, we have to multiply by the inverse of G, because that's part of the definition of the affine connection. It has a 1 over G in front. And then the 1/2, right? And so that's the Christoffel symbol, or the affine connection, with the usual convention that the first index is the one upstairs, right? And then the A and the B are the ones downstairs, right? And of course, we have to be very careful about where these indices are placed, right? So that we don't get confused, because whether an index is upstairs or downstairs makes a big difference, right? Because it gets multiplied to do the raising and lowering, and gets multiplied by the metric. So this is the definition of Riemann, which is straight out of the book, for example. And this happens in particular to be the definition we used in class, where in fact the first index is upstairs and the remaining 3 are downstairs. So we got to remember that, right? But other than that, it's exactly what I did in class. And so you have the gamma derivative of gamma term minus another derivative of gamma term, and then plus the gamma gamma minus the gamma gamma term, right? And you can check that this is in fact correct. And now, the next thing we need, of course, is the Ritchie tensor. And so that's defined in the usual way by contracting 2 indices, right? You see the 2 indices A here are the same. And so that's how you construct the Ritchie tensor and the Ritchie scalar. And finally, we take the difference between the Ritchie tensor and 1/2 times the scalar curvature to get the Einstein tensor out of that. So these are just the definitions. And there's really nothing to it, because you just use the definition and write them out, and it's just a matter of algebra of calculating all those derivatives and collecting terms, right? Now the problem starts when you try to write out what one of those things looks like. For example, the component of the affine connection, which has the upstairs index 1 and the 2 downstairs indices, which are 2 and 3, and you get with something that is, several pages long. Several pages long, because in particular it contains the inverse of the metric, which has that determinant, so it is quite a mess. And and then you can, well, at least you can verify that some of the symmetries of the affine connection and of the Riemann tensor are satisfied. For example, the affine connection is symmetric in the 2 lower indices. The Riemann tensor has the symmetry in the first pair and the second pair, and so forth. And well, as soon as you start to verify that, of course, the program sits there and thinks about it, because the expressions are quite complicated, right? I mean, there's some simplification you can do, and Mathematica doesn't know that those simplifications can be done unless you tell him explicitly and try to do them by hand, right? And well, it turns out that where it really chokes is when you try to verify that the Bianchi identity is satisfied. because the Bianchi identity is just, again, a covariant derivative of the right-hand side of the field, the left-hand side of field equations. But that is a messy thing. And so I actually found out that it sits there for quite a while. It should be automatically be satisfied, but it sits there for quite a while and tries to see whether that's actually true or not. And so then we're going to kill that and move on to the next one, which is the Shortcharge solution, right? Now, for the Shortcharge solution, the metric is given, right? It's not the most general form, so it is just, can you read that? Well, yeah. So it's this B function of R, and is the A function, and then the solid angle part is just trivial. And so, in fact, you can just write down the metric explicitly, right? It's a diagonal one. Calculate the inverse, which is trivial, and then calculate by exactly the same formula as I had before, the Christoffel symbol, and from that the Richie tensor, the Ritchie scale, and the Einstein tensor. So we're going to do that, and so evaluate notebook. And now in this case, of course, it goes at lightning speed because the metric has such a simple form. And so you can actually, in this case, as you can see here, you can actually write down all the, sorry, we're already at the Ritchie scalar. Where am I? You can actually write down the components of the affine connection. Most of them are zero. There's just a few of them that are non-zero. You see how many zeros there are because of all the symmetry that this metric has. So the calculation here proceeds almost instantly. And even the Ritchie tensor, because the metric is diagonal to start with and has a simple form, the Ritchie tensor itself is diagonal, right? So the only non-vanishing components are the ones that are along the diagonal. So this would be the TT component of Ritchie. This is the RR component of Ritchie. And then, well, it turns out that the other components are actually proportional to the previous one. So you don't even need to look at the phi, and theta components of the field equations. You can just focus on the first two. So basically what you need to look at is these two equations. So you have two equations, RTT equal to 0 and RRR is equal to 0, and two equations for two unknowns, which are A of R and B of R, right? And so that is what is done, right? So now we can solve those equations. I mean, as an exercise, you can write also the Ritchie scalar, for example. And if you want, you can write the Einstein equations as well. But of course, I told you that it's enough to just solve the equation for the Ritchie tensor equal to 0, because we have a source term that's 0 everywhere except at the origin, right? But in any case, the Einstein's equation for the various components look like this. And so the theta and phi components are actually proportional, so in such a way that if these two are satisfied, the RR and TT, then these other ones are satisfied as well. So now what one realizes at this point, right, is that you get a solution if A of R is equal to 1 over B. So there has to be a relationship between the two functions, that one is the inverse of the other one. And that then gives you a single equation for one of the two functions. So for example, for R, right? So that's the single equation that we want to solve. And now you make an ansatz. Either you find some way for obtaining a solution, or you just, well, we know what the solution looks like. So we're going to write it as 1 minus a part, which is, so 1 minus 2 mg over R. Now you do remember that the metric, right, we do know that G naught naught, right, is equal to minus 1 plus 2 phi, right, in the weak field limit where phi is the Newtonian potential. So if we have a point source at the origin, then this has to match up with whatever we have there. So in other words, this phi has to be equal to minus mg over R, right? And so that means that G naught naught, which you remember is this B function, right, has to have a term which is 1 minus 2 mg over r, right? So that is what the reasoning why we write the function a, which is the inverse of b, as 1 over 1 minus 2 mg over r, plus an extra piece possibly, but the extra piece, of course, will turn out to be 0. So we don't need to have that. Unless there is a lambda term, then we need that. So now you can write out what these a's and b's look like. And so the conclusion is that in order for the metric to satisfy the field equations, a and b have to be like this, right? So b has to be 1 minus 2 mg over r, and a has to be 1 over b. And if you use those, then the field equations are satisfied. So in particular, the Richie tensor is now exactly 0, right? So we have found a solution, right? And you can verify, of course, the Einstein tensor is also 0. And you can verify also that the Bianchi identity is 0, and everything is good, right? So it turns out that this is a solution to the field equations, which, by the way, is an exact solution, right? So we did not assume in any way that the field was weak, except in trying to determine an integration constant of the equation, right? Because this m or mg turns out to be an integration constant. We want the field away from the source to be a 1 over r Newtonian type field, right? So that fixes the coefficient and tells us that this coefficient of the 1 over r term has to be mg, right? But other than that, this is an exact solution of the field equations, which is remarkable, right? And as a consequence of the fact that it is an exact solution of the field equations, we also see that it is singular, right? Something is going on when r is equal to 2 mg, because you can have then that the b is 0 and that the a is infinite, right? So the other thing you can work out with this notebook is, for example, all the components of the Riemann tensor, right? Now you do remember that in order to solve the field equations, you just need that the Ricci is 0, right? But the Ricci, of course, is just some sort of contraction. It's like a trace of the Riemann tensor. So you might wonder whether actually the Riemann tensor is also 0 always, right? And the answer is no. The Riemann tensor is not 0, right? So, and that means that there is curvature, right, somewhere, because the components of the Riemann tensor are not always 0, and you can actually tabulate them. And in this case, this goes pretty quickly, again, because there is so much symmetry to the metric that many of the components of the Riemann tensor are 0, right? But there are certainly some which are not non-vanishing. So even though the Ritchie tensor is 0, Riemann is not. And you can finally calculate things like the scalar curvature squared. Well, that is going to be 0 because the Ritchie scalar itself is 0. The Ritchie tensor, when you square it, that's also 0 because it was 0 to start with. But Riemann squared is not 0. So when you contract Riemann with itself, then, of course, that is not 0, and it goes like 1 over r to the 6th. So there is, in fact, a singularity at the origin, which is not unexpected because we have a point source there. So you can calculate all these things, and you can imagine that you know, for general relativity, classical general relativity, not even talking about quantum theory, right? For classical general relativity, this, of course, is extremely useful because you know, you really, well, you can, but you really don't want necessarily all the times, you know, spend weekends raising and lowering indices and trying to figure out whether the damn thing is a solution of the field equations or not, right? It can be an immense amount of work. Only in the very simplest cases you do find that you can get a solution quickly, right? So computer algebra, you can imagine, is really an essential, has become an essential ingredient, right, in classical general relativity and certainly also in the quantum theory, right? Because doing calculations by hand is extremely tedious, and if you do them by hand, you're going to get an answer, but the question is, you know, is it an answer or is it the answer, right? Because if every time you redo it, you get a different number or different answer, then that's not very useful, right? So you want to get the correct answer and not do too many algebraic mistakes. And of course, Steve Wolfram's program is very useful in helping us out going through this maze of indices, right, and doing these things correctly. So it's nice, and so as an application here we have seen the simplest possible metric that you can look at where you can do these calculations almost instantly, right? And now, nevertheless, nowadays, the program I showed you, which is one that I wrote to just do this simple manipulation based just on the definition of you know, the inverse metric and the affine connection and so forth, you can just write them out. It's not, what I just used is not a black box program because we just wrote it out explicitly as a simple, you know, matrix multiplication and derivative type of thing where everything was explicit. Nevertheless, if things get complicated, then at some point, you know, you might want to use something that is a little bit more sophisticated. So this is a package that I used, which is called exact, right? And exact, right? And so this is a fairly recent one, and that is specifically designed. It's something that, of course, runs on top of Mathematica, and is explicitly designed to do the kind of algebra that you need in GR or classical, in quantum gravity as well as supergravity and problems where you do encounter significant amount of algebra and stuff that you don't want to do by hand because the likelihood of doing a mistake is very high. So I'll just evaluate this notebook. We're basically pretty much out of time. So it's loading this package. And it opens a window because that's a signal that it actually started successfully. And you're supposed to minimize this thing. And so this is a much fancier program that allows to do all sorts of neat things. And I'll show you one example here. This was just a test run of something that is not physically particularly relevant or interesting, but it did have some of the ingredients of a calculation that I was interested in doing, which was basically cosmology with G of box with a running gravitational constant. And so what happens in this case is that you see it now allows you to actually write covariant derivatives. You see this symbol, the nabla is actually not an ordinary derivative, but a covariant derivative, right? So it contains the affine connection terms. And in this case, you actually calculate the Lambertian. So it's the covariant derivative times itself, one index up, one index down. And this object is defined within this package. And then it acts on the scalar curvature, right, which is R. And you can have this box term act several times, which is done up here. So you can have it act, in this case, 4 or 5 times. And then you can write all these terms out, and you can try to construct an action that contains this box of R terms for reasons that I don't want to get into. And so you end up with an action that is something like this, right? And now, what this program then allows you to do is, if I have an action, it can do the variation. And that's what is done here, because this is the variation of the Lagrangian. So you take the action, you do the variation. As soon as you do the variation, this action is actually simple in structure, but the equations of motion you get are fairly complicated. So you get all sorts of terms. So you get all this rubbish, right? And so that's the equation of motion from the variation. And now the package is clever enough that, of course, well, being, coming from the effort of a number of different people in Europe mostly that have worked on this for several years, it knows about all the identities for the Riemann tensor, the Richie tensor, the Bianchi identity, total derivatives, you name it, right? And so the next step is to tell him to actually simplify all of this using known identities. And so that is what is done here, right? Is to do a simplification of this using properties or using all the rules. So now it shows you all the rules it is using to try to bring this down to a more manageable form. And this is in fact what it gets. If you look at the expression we had before and what we have here, it is significantly simpler. So these are actually the equations of motion. I can't get it all on one screen. I mean, I can't get the whole expression to show on the screen, but this is what you get after you vary that fairly simple and innocuous looking Lagrangian at the beginning and then applying all the simplification rules. So the message here is that nowadays, if we can avoid it, we don't want to do a lot of that index manipulation business by hand because it is very complicated. It gets out of hand very quickly, right? And so in order to actually get correct results, results that we can believe and others can believe, we often resort to computer algebra because clearly in general relativity there's massive amounts of computer algebra that will come in at some point for certain types of calculations. And in fact, one funny thing is that when these people wrote this program, the first thing they did is they went around and looked for papers on the internet and checked them, right? Trying to find mistakes. So they went back a few years, trying to find papers where, certain field equations had been obtained and then, simplified. So they were looking for mistakes. And of course, they did find quite a few, right? Because as I said, if you do it by hand, there's always that risk that something will go wrong somewhere, because you haven't had sufficient number of cups of coffees and things like that, or it was late in the evening. So here you're usually guaranteed that you will get a reasonable answer. I mean, there can be, of course, a bug in the program, and there's always bugs that come up here and there, but at least the simpler stuff is by now well established. So anyhow, that's enough for today, I guess. And you had a question.
You answered it.
Oh, yeah, I answered it. Good, excellent. Okay, all right, so see you on Thursday then.